4.2, we're going to be talking about a couple of theorems. So the first one we want to talk about is Rolle's theorem. And Rolle's theorem says if f is a function that satisfies the following three hypotheses, f is continuous on a closed interval ab, f is differentiable on the open interval ab, and f of a equals f of b, then there is a number c in ab such that f prime of c has to equal to 0. So a picture is really worth 1,000 words in this case. So if we take a look at what this is telling us, is we have a continuous function that's differentiable, and we're told that if f of a is the same as f of b, then at some point in between, the function has to have 0 as a value of its derivative. Well, if f of a and f of b are the same, then that means either it's a horizontal line, because then it would be equal the whole way through, that it goes up and comes back down to the same point, so it would have a local maximum, in which case its horizontal tangent would have slope 0, or it goes down and comes up, in which case then it would also have a horizontal tangent whose slope is equal to 0. So really that's the idea of what Rolle's theorem says, is that if a function is equal at the two endpoints that on some closed interval, then at some point it had to stop and turn around, because it either went up and had to come back down, in which case it had slope 0, or it went down and came back up. It says at least one exists. So if you look at the one in the middle, there would actually be two in that case, because it went up, came back down, and came back up, and that's okay too. But this is just an existence theorem that says at least one of them exists. So mathematicians love their existence theorems, because we often want to talk about things that we don't explicitly want to or can't find. So let's take a look at a couple of examples of how we can use Rolle's theorem. So let's apply Rolle's theorem to the position function s equals f of t of a moving object. If the object is in the same place at two different instances, t equals a and t equals b, then f of a equals to f of b. Well, what does that tell us? So if f of a equals f of b, so let's imagine here's our object, here's our number line, here's a, right? And we know, here's our graph, so here's a, and over here we have some point b. So our function does something, but what do we know about f of a and f of b? They're the same. So then, if our function looks like this, what does that tell us? Well, it says there exists at least one point c such that f prime of c equals to 0. Well, if f is a position function, what's the derivative of position? Velocity. So what does that tell us? That at some point, its velocity was 0. Well, if you start and stop at the same place, what does that mean? At some point, you had to stop and turn around, right? Because if I was here, and I'd get up and walk over there to come back to my chair, I'd have to stop, turn around, and come back, right? So that's what Rolle's theorem tells us in this situation, is that if you begin and end at the same place, at some point, you had to stop and turn around. All right, let's take a look at our next example. So this one is something mathematicians love to do. We want to prove that this equation has a solution, and it has only one solution. So cubic equations, we know, can have up to 3 solutions, right? One for each exponent. We want to prove that this equation has exactly one real solution. So to do that, we're going to do this in two different parts. We are going to prove that it has at least one solution, and then we're going to prove that it can't have more than two or more solutions. Because if it has more than one, but less, one or more than one, but less than two, what's the only number in between? One, right? So let's break this down. So since f of x is continuous, and that follows from the fact all polynomials are continuous, and if we calculate f of 0 is 0 cubed plus 0 minus 1 equals negative 1, and f of 1 equals 1 cubed plus 1 minus 1, which is 1. So that gives us that f of 0 is negative 1, and f of 1 is 1. So then, by the intermediate value theorem, there exists a number C in the interval 0, 1 such that f of C is equal to 0. And that follows from the fact that since f of 0 is negative 1 and f of 1 is 1, so we have this function and we know it's continuous. We know at 0 it has value negative 1, and we know over here at 1 it has value positive 1. So since it was continuous, we know it couldn't jump over the x-axis, so there had to exist some number c by the continuity of the function where it crossed the x-axis, so it's equal to 0. Right? That's the intermediate value theorem. So that proves that there's at least one real 0. So therefore, f of x has at least one real 0. So note, it just says that there's at least one. We don't know. It could go up and down like 20 times between 0 and 1, right? So now we want to do part 2, which is we are going to show that f can't have 2 or more zeros. So to do that, to show that it can't have 2 or more zeros, we're going to assume that it does have 2 and show that that leads to an impossible situation. So this is called proof by contradiction. So we assume f of x has 2 zeros. We're going to call them m and n. So then that would imply that f of m is equal to 0 and f of n equals to is 0. Well, if f of m equals 0 and f of n equals 0, we know that polynomials are continuous everywhere. So we are going to satisfy all of our stuff for Rolle's theorem, right? It's continuous on the closed interval, it's differentiable, because polynomials are everywhere differentiable, and f of m equals f of n. So by Rolle's theorem, there exists a C in the interval Nm such that f prime of C is equal to 0. So far it doesn't seem like anything too weird is happening. Let's calculate f prime. So f prime in this case, so the derivative of x cubed plus x minus 1 is 3x squared plus 1. Well, now we have a little bit of a problem. So what is the smallest value of this? Well, we know x squared is always greater than or equal to 0, right? So the smallest x squared can ever be is 0, right? So then the smallest f prime can ever be, so then f prime of x would always have to be greater than or equal to 3 times 0 plus 1, which is equal to 1. Well, f prime of x is always greater than or equal to 1. This contradicts f prime of c is equal to 0, because 0 is less than 1, right? Therefore, f can't have 2 zeros. Because if f is allowed to have 2 zeros, the function would have to turn around and come back down and touch the x-axis again. But if its derivative is always bigger than 1, that means it's always going to be going up and always have a slope of 1. So it's going to go through the x-axis exactly 1 time. So we've now proved that this equation can have exactly one and only one solution. So this is an example, once again, of what's called an existence theorem, right? We proved that something existed and we didn't actually find it. And we proved that it's unique and there's only one. This is often helpful later on in advanced mathematics, where we need to prove that some object exists, but we don't necessarily need to know what it is to prove a further statement. So we've found and proved existence of an object without having to quantify what said object is. And that can be useful if you've taken philosophy and ever done logical arguments. You'll do things like this all the time, where you postulate the existence of objects. If you can prove they exist, you can then use them to further arguments. So advanced mathematics is a lot like philosophy, actually. So they kind of have this intersection where we do a lot of stuff using logical deduction and induction. And so we need to prove things exist or don't exist or can't exist, right? And those are all useful things to have at our disposal. All right. So now we are ready for Rowley's theorem's extension, which is called the mean value theorem. So Rowley's theorem can be used to prove the following important theorem. So note, that's what I was just talking about. Rowley's theorem and the mean value theorem are both examples of existence theorems. They guarantee a number exists, but the theorem does not give a method to find the number. We will actually use the mean value theorem to prove the crown jewel of Calculus 1, which is called the fundamental theorem of calculus. So the mean value theorem is necessary for this. And you'll love the fundamental theorem of calculus because it's awesome. But we won't get there until chapter 5. So the mean value theorem states the following. If f is a function that satisfies the following two hypotheses, so not three, like Rowley's theorem that says f is continuous on the closed interval ab, is differentiable on the open interval ab, then there exists a number c in ab such that f prime of c is equal to f of b minus f of a all over b minus a, or equivalently, f of b minus f of a is equal to f prime of c times b minus a. What this states is that, once again, it's best summed up with a nice picture, is that if you have a continuous function on a closed interval, there exists a point C in between A and B where the slope of the tangent line is equal to the slope of the secant line through the points A and B. Right? So if you have your secant line going through f of a, f of a, f of b, then there exists at least one number c where the tangent line at that point C is parallel to the secant line connecting those points. So in other words, at some point in the interval AB, the instantaneous rate of change is equal to the average rate of change on that interval, at least once. So the average velocity has to equal the instantaneous velocity at least one time. All right. So you can read the proof if you're interested, but we're not going to focus on the proof. So let's take a look at example number 3. Consider f of x equals x cubed minus x with a equals 0 and b equals 2. Find the value of c in the interval 0, 2 that satisfies the mean value theorem. All right, so first thing we're going to need to do is find our derivative. Well, find our derivative and find our slope, right? So the secant line has slope f of b minus f of a all over b minus a. So our slope is going to be f of 2 minus f of 0 all over 2 minus 0. So that's 2 cubed minus 2 minus 0 cubed minus 0 all over 2 minus 0. So 2 cubed is 8 minus 2. The rest are 0. So that gives us 6 over 2, which is 3. You don't have to do any of this by hand, right? You could have just punched that in your calculator to get 3. So then we want to know where the slope of the secant line is equal to the slope of the tangent line. So the tangent line has slope f prime. So we take our derivative. The derivative of x cubed minus x is 3x squared, take away 1. So to find this point, we're going to set f prime of x equal to the slope that we found of the secant line. So in other words, 3x squared minus 1 is equal to 3. So we add 1, we add 1. We get 3x squared equals 4. Divide by 3, divide by 3. We get x squared equals 4/3. Take our square root, and x is equal to plus or minus, the square root of 4 is 2, over the square root of 3. So plus or minus 2 square roots of 3 over 3. We're only concerned on the interval 0, 2, so we don't need the negative solution. So the value of c is the positive root and we reject negative 2 square roots of 3 over 3 because it is not in the interval 0, 2, right? So the smallest value in our interval is going to be 0. So that would be the point where the slope of the tangent line is equal to the slope of the secant line. So in order to find the number c, you would take the derivative, find the slope of the secant line, make them equal, and then solve for the inputs. There can be more than one, right? In this case, if our interval was bigger, there would have been more than one solution. But we only take the one that's in the interval in question. Yes?
If you guys know one thing, there's a positive and a negative, or maybe like there can be multiple positives?
There could be multiple. They can be anything. It just depends. Right? In this case, there was positive and negative because we use the square root property. But it could have been a polynomial that would factor and both solutions were positive. Or both could be negative. It doesn't, there's no hard, fast rule on that. They can be anything.
So, on the interval, if it was less than 0, and
so the next example is if an object moves in a straight line with position function s equals f of t, then the average velocity between the points t equals a and t equals b is f of b minus f of a all over b minus a. And the velocity at t equals c is f prime of c. So then by the mean value theorem, it says that at some time in the interval ab, the instantaneous velocity equals the average velocity. So for instance, if a car travels 300 miles in 5 hours, then at least once the speedometer must have read exactly 60 miles per hour, right? Most likely you were going faster or slower most of the time, but at least once it was at exactly 60 miles per hour. In general, the mean value theorem can be interpreted as saying that there is a number at which the instantaneous rate of change is equal to the average rate of change for every interval. So the mean value theorem can be used to obtain information about a function from its derivative. So suppose that f of 0 equals negative 3, and we know that f prime of x is less than 5 for all values of x. What is the largest that f of 2 can be? Okay. Well, one form of our mean value theorem said that f of b minus f of a was equal to f prime of c times b minus a. Well, let's let a equal 0. Then f of 0 we know is negative 3. Or in other words, f of a is negative 3. We know that f prime of c is less than or equal to 5. We want to know, well, what's the largest f of 2 can be? So in that case, we would have b equals 2. F of 2 is the question mark. This is what we want. So then that would tell us that f of 2 minus f of 0 is equal to f prime of some value of c times 2 minus 0. So we know f of 2 is what we want. F of 0 is negative 3. And now we have f prime of c we know is less than or equal to 5. So then this statement right here would have to be less than or equal to 5 times 2 minus 0. Because if f prime of c is less than or equal to 5, we know the biggest it can be is 5. So f prime of c times 2 minus 0 has to be less than or equal to 5 times 2 minus 0. So then this is less than 5 times 2 minus 0. So then f of 2 plus 3 is less than 10. So we minus 3, we minus 3. And we have that f of 2 would have to be less than or equal to 7. So the biggest value that f of 2 could possibly have would be 7. Well, what is this saying in terms of physical reality? Well, think of this as where we start, and this is our speed or our velocity. So if I start at the point negative 3, and the fastest I can go is 5 units per second, how far can where will I be in 2 seconds? Well, the farthest I could go is 2 times 5, which is 10, but I started at negative 3, so negative 3 plus 10 is 7. That's as far away as I could get. So if you know something's maximum velocity, you know the furthest away it can get. That's what the mean value theorem is telling us. Is if we know things about something's rate of change, we can infer information about the original object. Turns out there's a lot more to that statement than we're letting on right now. And that's a whole other class, but that's the basic idea of what this is telling us in this case. All right, so let's...
No, at least you tried though, that's the thing.
Let's go ahead and work this. So to find the slope of our secant line, we would do f of 0, which is 0 plus sine 0, gives us 0. And f of 2 pi would be 2 pi plus the sine of 2 pi. But the sine of 2 pi is also 0, so we just get 2 pi. So our slope is 2 pi minus 0 all over 2 pi minus 0, which gives us 2 pi over 2 pi, which is 1. So then we find our derivative. F prime of x is 1 plus cosine x. And we need to make f prime of x equal to the slope of our secant line, which is 1. So that gives us 1 plus cosine x is equal to 1. So we minus 1, we minus 1. And we get cosine x is equal to 0. We take our inverse cosine, and the inverse cosine of 0 is pi over 2 and 3 pi over 2. So those would be our two values of c. So let's draw a picture of this on our calculator.
Do you think it'd be useful to like memorize the entire unit circle? You know, like this? find that on the
Absolutely.
We need to do that now.
So we have x plus the sine of x. And if we were to, let's change our window. Let's make our x min 0, our x max 2 pi. And let's go with, I think our y min should be like 0. Let's do y max 4 and let's scale it in 0.2s. So I didn't quite make it. So window, we need to make our y max a little bigger. Oh yeah, it's got to be at least 6.28. So let's make it 7 and we'll scale it in 0.5s. All right.
If you could write that in like an f of a and f of b formula, what would that be?
Well, we're going to draw some lines and then we'll talk about some different things. So let's draw our picture first. So the slope of our secant line is, let me actually switch this. Let's use the exact values because it'll make it easier. So let's go window. Oh, our x max is 2 pi. Just kidding. So we're perfect. Okay. So then the slope of the secant line is going to be the one that goes through these two endpoints. And at pi over 2, so pi over 2 is like 1.5. So there's some point here where those lines are parallel, and then there's another one like right here where they're parallel. 3 pi over 2, right? So in terms of the other version of the formula, you wanted it like this, so it would be f of 2 pi minus f of 0 is equal to f prime of c times 2 pi minus 0. And you're solving for f prime of c. But in this case, that's the harder way to do it. We wanted the other equivalent form because we're actually looking for the input for f prime of c. You'll get the same equation if you use that. You'll just do a couple more steps of algebra to get from A to B. So our theorem says if f prime of 0, or if f prime of x equals 0 for all x in AB, then f is constant on AB. So there are a couple things we want to take note of, so some symbols. We have what is called the Universal Quantifier. That's this guy. And this is an abbreviation for all or for every. And it has another one, which is represented by an backwards capital upside down E. And this is called the Existential Quantifier. And this one is there exists. So the upside down A is the for all or for every. And the E, or the backwards capital E, is that there exists, so the universal and existential quantifiers. So we use these as abbreviations in mathematics because those statements come up a lot. So for instance, f prime of x equals 0 for all x in AB. So if f of x equals 0 for all x in AB, then f is constant on AB. So basically this is telling us if a function's derivative is always 0 on some interval, then the function values can't change on that interval. The corollary is actually a bit more interesting. It says if f prime of x equals g prime of x for all x in an interval AB, then f minus g is constant on AB. All right. So let's go ahead and use that in a way that you probably wouldn't expect. So we wish to prove the following identity. So note, this can be used to prove a bunch of trig identities too, which is kind of nice. Because then you just take derivatives and show that they differ by constants, and then find the constants as needed. So in this case, if we identify f of x as inverse tangent of x, and we identify g of x, I'm going to write it as the negative cotangent of x. And we'll see why in a second. Then f prime of x, the derivative of the inverse tangent is x squared plus 1. G prime of x, we have our negative comes down, and then the derivative of cotangent is negative 1 over x squared plus 1. So the minus minus makes it positive, and we get 1 over x squared plus 1. So f prime of x is equal to g prime of x. Therefore, which is also as an abbreviation of 3 dots, right? Therefore, f of x minus g of x has to equal a constant. So here's my f and here's my g. So that tells me the inverse tangent of x minus inverse cotangent of x has to equal a constant, and we'll just make that c. Our minus minus becomes a plus. Well, this has to equal some constant, so we can find that constant by using any value of x. So let's use x equals 1. So then the inverse tangent of 1 plus the inverse cotangent of 1 is equal to c. Well, the inverse tangent of 1 is pi over 4, plus the inverse cotangent of 1 is also pi over 4, equals to c. So pi over 4 plus pi over 4 is 2 pi over 4, which is pi over 2, is equal to c. Therefore, the inverse tangent of x plus the inverse cotangent of x has to equal 2 pi over 2. And our identity is proved. So the inverse cotangent of x plus the inverse tangent of x equals pi over 2 for all x. And we got that by using the fact that if two functions have equal derivatives, then their difference must be a constant. So, fun bonus fact. So what if we did something similar with f of x equals sine squared x and g of x equals cosine squared x? We'll do it negative, right? So then f prime of x is equal to, by the chain rule, 2 sine x cosine x, and g prime of x is equal to negative 2 cosine x times the derivative of cosine is negative sine x. So then g prime is equal to 2 sine x cosine x. So f prime of x equals g prime of x. So f minus g equals a constant. So then that would tell us that sine squared x minus a minus cosine, so plus cosine squared x equals c. And if we let x equal 0, we have sine squared of 0 plus cosine squared of 0 equals c. Sine of 0 is 0, cosine of 0 is 1, 1 squared is 1 equals c. Therefore, sine squared x plus cosine squared x is equal to 1. Oh, that's our good friend, the first Pythagorean identity. Right? So, we can use calculus, the mean value theorem, to prove a whole bunch of trig identities in a very different way than we learned in Math 187, right? So if you had two big messy things equal each other, you would take their derivatives and subtract. And if you get something, if you can make their derivatives equal or opposites of each other, right, then we could use this theorem to prove that identity, right? So just like we did here with sine and cosine, we essentially made the identity work.